All right, so today we're continuing with this transition. We talked about exponential functions. All right, when we talk about exponential functions, remember we're looking at something that is a function, but not only is it a function, all right, we looked at the fact that as we look at these graphs, that they're also one-to-one. So make sure that's kind of what we're picking up from Fridays, that, hey, since it's one-to-one, we have an inverse. With that inverse, we did look at a graph where here, this is the exponential function. And this is just me switching all the X and Y values in the ordered pairs we use to get to the inverse function. All right, now the inverse function, this is where we introduce logarithms. Okay, so we're now going to be focused on logarithmic functions. We want to make sure we're comfortable getting between the two, but also there's some things that we're going to have to set in place dealing with logs. Today, we're going to focus on getting some inverses, some basic operations as far as dealing with graphs and such. And tomorrow we need to go into properties. So no, today and tomorrow, some foundational stuff when it comes to logarithms. With that said, getting from a logarithm to an exponential helps with understanding what the logarithm is. But we also need to be able to get from an exponential to a logarithm as well. Okay. So with this statement here, if we're saying 4 is equal to the log base 2 of 16, what is the exponential statement that is equivalent to that? That is the inverse of that. What are we actually focusing on is definitely an important part. What sets the focus of that logarithm right now? Huh? The argument's important, but what tells us kind of the focus of the logarithm? The base. When we do logarithms, you need to focus on the base. All right. Now, is every logarithm going to have a number down there at the base? No. Make sure you understand that as we deal with this, we can often see the base, whatever the value might be. Right. In this case, it was base of 2. If you see the word log and no base, that's going to be a common logarithm. So what is the base? Right. And then if you see ln right here, right, that's what we call a natural log. And we put ln just kind of make sure to separate it from the common log. But that's going to be where we have base e. So anytime you see ln, hey, that's a logarithm. It just happens to be base e. So keep that in mind. Here, though, with this first one is base 2. So understand that when I go rewrite this, I'm going to put 2 equal to something, right? Make sure you see here, since the 4 is by itself, that's going to be what becomes the exponent. And the argument is going to be what's by itself now. Okay. Now, what is 2 to the 4th equal? 16, right? So make sure you see here the logarithm, when you see log base 2 of 16, it's looking for the exponent. All right. 2 to the 4th power is what gives us 16. That's why the logarithm equaled 4. Okay. Now, those are great because you kind of see a statement that is true, right? We're just rewriting in its different forms. But the next two is dealing with, like, say I'm having to graph something, I'm trying to solve something. This is where we're going to need the inverse statement to help us work through that. Okay. So how can I change the second one here as far as having an equation with 2 variables? I'd already rewrite that. So the 5 needs to move, right? Still the base, but now it's the base of an exponential. Okay. I understand that's going to be helpful because, like we said, when we write the inverse statement, it's going to help you with inverses themselves, right? Exponentials are 1-to-1, logarithms 1-to-1. So going back and forth is definitely something that we're going to work on as we deal with these things. Okay. Now, what's special about that third one I did down here, though? It has an e, right? So when I go to convert this to a logarithm, what should I use? ln, right? So we'll say, hey, x plus 9 equals the natural log of 100. Okay. Now, one thing I will point out here on the software, you'll often probably see something with the parentheses. That's fine, right? It's good to understand that whatever immediately follows, though, is going to be the argument. Okay. So on your calculators, you'll definitely need parentheses, but understand that, like, writing by hand, hey, if there's only one thing behind the ln, that's going to be the assumed argument right behind it. Okay, so like if I gave us the ln of x squared, well then, hey, x squared is the argument of that natural log. So keep that in mind. Now, the reason we like that one though is, hey, I can just subtract 9 from both sides and I got a solution. Not much I could do with it because natural log of 100 is going to be an irrational value. Okay. So we're going to find here, just sometimes you're just going to have to leave it as it is. Okay. Any questions here? Do we feel okay with like the idea of the bases moving around? All right. Then the one thing I would say, just kind of a reminder, don't forget to watch out for base 10 and base E, right? Like I did the natural log here, but I could have put, 10 to some power and did a common log, right? So keep an eye on this. I guess I don't need this anymore, so trash that. But we're going to move on to the graph now. Okay. Now, as far as the graph is concerned, we talk about transformation, so I'll start there, but also understand we kind of have in place now to deal with like finding the intercept. So let's look at that as well. Now, as far as this function is concerned, what is the parent function? What like we deal with exponentials, what's something that is important that we need to identify? X is in the exponent, right? That's the one thing we want to identify, but we can't just say any exponent, right? Make sure, again, you see here the importance of identifying your base. Whether it's exponential or logarithmic, you need to pay attention to the base. So here we just like, hey, the parent function is 2 to the x. And if you need the table, fill out that table, right? Remember, do -2, -1, 0, 1, and 2, and 2 to each of those powers. I'll give us an idea of what the pattern is, okay? But we're not graphing 2 to the x, right? We have -5 plus 2 to the x plus 3, or x minus 3, sorry. With that said, then we need to identify our transformations. So we're going to look at some horizontal transformations and some vertical transformations. What is someone getting here? All right, that -5 is important, right? Is it going to shift it left or right or up or down? All right, that's a vertical shift, right? It's outside of the exponent. So this is going to be like, hey, we're shifting down 5. All right, that 3, however, then is going to be a horizontal shift. Which way do we go, though, for x minus 3? Since it's in the exponent, right, inside our focus, make sure you remember you're doing the opposite. Now, as far as transformations, that's our main thing. But what's something important that I said that we should always identify first, since we know we're working with exponential? My hint would be we need it for rationals as well. It's asymptotes, right? So there are some restrictions, but keep in mind that when I say restrictions, I'm normally thinking about like input values. So exponentials, what's the domain? What's the domain of of this function here? So like if we were over here and we're just kind of making a note that, hey, the domain of f, right? Hey, that's all real numbers. Okay. Now the range is restricted, but that's where the horizontal asymptote. So make sure you see here another great thing to state here to be like, hey, there's a horizontal asymptote at y equal to -5, coming directly from that vertical shift. And I definitely recommend graphing that first. It's not a part of my graph, but hey, it definitely helps us set where to start. If you remember, this is where I said, hey, once you get that in place, go over here and just kind of give yourself a little mark that says, hey, this is what my horizontal shift told me to do. Now, the reason I do this is we're not going through that point, right? However, I could treat it like the origin. If you get stuck, remember, go back and look at the graph of what we did here. What's 2 to the 0? All right, well, if I plug in 3 instead of 0, I get 3 minus 3, which is 0, right? 2 to the 0 would still give me 1. -5 plus 1, well, isn't that 1 above -5? Right? The main thing, if you remember, as I told you, if you get stuck, use this to focus a table, right? Build yourself a table, put 3 on there for the x value, and then go put 2, 1, 4, and 5 and plug in the values and you'll get what you need. Okay, there's no need to stress about it. Build the table if you need to see what's going on. But remember here, this is 2 to the 0, so it's just one above this little imaginary origin that I put here. This is not the origin, it's just us focusing on transformations. Okay, from here though, why did I put this point? How far up is that from my horizontal asymptote? Everyone see I just went up 1, 2. Well, what does 2 to the first power equal? 2, right? There's no stretch or shrink here, right? I can do exactly what it's supposed to. Now, as far as that, the only other point I definitely recommend getting is the 2 squared point, right? So if you plug in 3, 4, and 5, you'll get these nice integer values. That's the nice thing about 3, 4, and 5. Just know if you plug in 1 and 2, you're going to get fractions. Now, with a base of 2, that you can, a decimal is still a nice thing to work with. Just know that you'll get negative what, 4.5 and negative 4.75. So where I'm getting that from, those a half and a fourth. Okay, and we can draw our graph. Oops. Now, how's the horizontal asymptote help us? What's the end behavior over here? What's it going to approach? It approaches the horizontal asymptote. That's what it's for. Okay. So know that as we go to the left-hand side, as you go to the left-hand side, the function is going to approach whatever you're in. This case, the function approaches the asymptote because we have exponential growth. Okay. As we approach positive infinity, that's where you're going to see the growth without bound. Okay, that's where we're going to highlight exponential growth. This highlights the horizontal asymptote here. So this is my horizontal asymptote. And then over here is the exponential growth. Okay. With that said, though, let's look at our intercepts because, hey, we got some stuff in place to kind of talk about intercepts. So understand, hey, you could definitely plug in 0 for x. So like looking at f of 0. All right, you get 2 to the negative 3. Well, if you look at that, 2 cubed is 8, right? So it's negative 5 plus 1/8. All right, so that's going to give us what, negative 4 7/8. So it's going to be a pretty small number, pretty close to negative 5, right? Understand again, though, that is what we see here. It's not quite negative 5, but it's pretty close. Now, the one that we have to be careful of is setting the function equal to 0. And this is where logarithms is going to help us. All right, because here I can add a 5 to both sides. But technically, I can't really go much further because as I showed you before, if this was a power of 2 instead of 5, say it was 8, as we just saw 2 cubed is 8, we could rewrite the 8 as a base of 2. We can't do this, but this is where that inverse statement will help us. All right, we could write this, not all the time, and we're going to work on this more today, but using the inverse statement, we could be like, hey, this is log base 2 of 5. And then all of a sudden you're getting to something that gives us an x value by adding the 3 to both sides. Now, where is this at? Well, hey, that's that value right here that we're focused on. Okay. Now, how do we know it should be kind of in that area? Well, what number is 5 a little bit more than that is a power of 2? What are some multiples of 2, y'all? 4. Right? If I kept going, it'd be 8. Well, isn't 5 just a little bit bigger than 4? So that log base 2 of 5 is going to be 2 point something because it's got to be more than 4. It's got to be 5. What's 3 plus 2? Isn't that just a little bit more than 5 itself here? And that's where we know that we're kind of in the right area. Okay. Now, I will say this, we're gonna cover what to do with log base 2 of 5 today a little bit more. But do know, I just want to make sure to show that we now have the ability to solve something that we weren't able to Friday. Okay, I should say Thursday because we were looking at this more on Thursday, but now we have the ability to moving forward. This is where the inverse statement definitely helps us out. Okay, now as far as graphing it, did I need that stuff? Not really, right? If you can use transformations, make sure you take the route of least resistance, right? That's definitely hopefully what you're taking from this. Focus on your transformations and you make it a lot easier for yourself. You didn't have to go through all this. But also know I could tell you on the test, find the intercepts. So we do need to remember, plug in 0, set it equals 0, and deal with what comes. All right. Any questions here are clear for somebody? All right, so let's look at this then. So everyone has this graph down? If not, make sure you copy it down because we're about to use it. So the reason I want to focus on this now is just to make sure we go back to dealing with our inverse statement, right? How do I graph an inverse? And what I want to build up to is just like, hey, once we're comfortable getting between an exponential and a logarithm, that's one way to deal with the graph of a logarithm. Just get the exponential, graph the exponential, and then invert it. That's one way to deal with it, okay? Now, I'm hoping today, after we look at this, we can be comfortable with graphing a logarithm just by itself using transformations as well, okay? But I feel like focusing on the inverse aspect is definitely important. So I have my graph here. One thing we can look at, as we've talked about, is the fact that it is 1-to-1, right? It only hits the graph one time, no matter where I put that horizontal line at. So that's why we know it has an inverse, okay? With that in place, let's go find that inverse statement. So I'm going to take this and I'm going to now use the inverse. Now remember, the main thing for an inverse is we're just switching X and Y. That is the inverse. Okay. But what do we have to solve for when I do that? What do we need to get by itself? We need to get Y by itself, right? So as we do that, make sure you understand that, hey, we got to do stuff like add the 5 to both sides. And this is where we get to the point of, okay, if I have an exponential, I have to rewrite it using a logarithm. Okay, so the statement that we can use here then is going to be focused on a logarithm. The base needs to stay what it was though. So I had a base 2 exponential. I'm going to use a base 2 logarithm. Make sure you see here though, parentheses will be very important because we want that x plus 5 as the entire argument that was over there. On the other side, we'll have y plus 3. And all we need to do is subtract the 3 from both sides. Now I'm putting the 3 first. So I don't want it to accidentally get inside of my logarithm. But make sure you see I made it -3 because I moved it from the side with the y opposite of that. Now, with that said, we could highlight some of the same things that we just saw. The big deal that we have to be careful of, though, is with a logarithm, the argument is the inside, right? That's going to be the inside part. That's where our horizontal shifts are going to come from, okay? So if we look at this from the transformation perspective, so we say, hey, I have a horizontal transformation, but this time it's a shift left 5. On the outside, we have a shift of down 3. Okay. Now, the tough part here is that I have to remember exponentials have a horizontal asymptote. Okay. But logarithms are going to have a vertical asymptote. We have to remember here that logarithms have a domain restriction. So when we look at the domain of a logarithm, make sure that you're reminding yourself that whatever the argument is, it must not be negative and it must not be zero. Okay, it has to be a positive number. So what we need to do is take whatever argument we have, in this case, x plus 5, and set it greater than 0. Solving that inequality by just subtracting the 5 from both sides will give us our domain. Okay, so that is our domain. If you write it using interval notation, we say -5 to infinity. All right. What you find there, though, is we could also get the asymptote out of that. So we would say, hey, there's a vertical asymptote, not a horizontal, but a vertical at x equal to -5. Okay. So I took the exponential function f, and I went over here, and this would be the inverse of that. So make sure you see that this is my inverse function. All right. Being that it's a logarithmic function, I still can do transformations. But one difference here that we have to be careful of is whatever the argument is, I don't want 0 or negatives in there at all. Okay, no zeros or negatives inside the argument. With that said, be comfortable with getting the domain, right? Set up the inequality to do that. As we've dealt with rationals, we've talked about square roots. This is our third one, right? So those are going to be the 3 that we want to watch for: x in the denominator, x under a square root, and then x inside a logarithm. Okay, so that's something that we want to focus on. Now, using the transformations, though, we can definitely build this graph. So the first thing we're going to put is going to be that vertical asymptote at -5. From here, though, I definitely recommend you take the same approach as I did the other one. Hey, I shift down 3, so let's go over here and just put a little, has nothing to do with the graph. I'm just helping myself focus on what's going on. Okay. Now, based on my domain, should I go to the right of the asymptote or to the left? So should I graph going this way or should I be going the other way? What does greater than tell us to do? All right. We want numbers bigger than -5, right? So we need to be going to the right from here. So I'm going to focus in down on this point here. And guess what? I'm going to use the powers of 2 still. Right? So I know that 2 to the 0 is 2, but I'm going to the right instead of up now. Okay. What you're seeing there is, what is log base 2 of 1? Now remember, the exponent that works for that, anything to the 0 of an exponent is what gives us 1. So that's going to be an important one we don't want to forget. So log base 2 of 1, right? It's definitely something we're focused on there. From here, though, make sure you see that all I'm doing is really just taking these points and I'm interchanging x and y. All right. Or did I mess up a sign somewhere? Yes, I sure did, y'all. No one called me out on that. All right, so we do have a minor error here that we got to fix. I'm going to tell you how I know my mistake. Hopefully you catching why I know my mistake. What's special about this function and this function down here that I stated? What are they to one another? Inverses. And all an inverse is interchanging what? What is this ordered pair here? It's like 3 -4, right? Well, if I interchange 3 -4, shouldn't that become -4, 3? Good news is I was a little off, but my main thing was here, that's definitely not +3. I went down instead of going up. Does everyone see that? That's an error on my part. Where was my error? Well, I didn't pay attention when I copied my problem. As you saw, I had to go change this sign up here. And I had to change it all the way down to make that a +3, right? That's because I just This is my own fault. I didn't pay attention to when I copied it. I didn't keep the negative. Okay, so I apologize for that. But make sure you see how I made a mistake and I'm able to catch that mistake. Like, hey, that doesn't line up with what I see over here. Okay, with that said, now that we have an up 3, I'm going to put that mark up here. Okay, that mark doesn't have anything to do with the graph again. It's just helping me focus. Now that's a lot better because now instead of being in the 4th quadrant, I'm in the 2nd quadrant, right? One sign's negative, one sign's positive. That's better. Okay. Now, with that said, though, I can go through and do as we were talking about. I could put that point there. That's where log base 2 of 1 is kind of the focus, right? I'm actually plugging in -4. Well, what's -4 plus 5? There's where the 1 comes from. Okay. From here, though, make sure you see you could just take each of these points and flip the ordered pair, right? So like this one here is what, 5, -1. So we're going to plot -1, 5. Look how far away from the graph that the horizontal, the vertical asymptote, sorry. Isn't that 4 away? Isn't that the same as saying log, like the 2 to the 4th, sorry. It's still the same as 2 to the 4th is what I'm trying to say. What we're going to find here, then this one's going to be 2 away. There's my half, there's my quarter, and I get my graph. So look like that. Now make sure you see here, this is kind of the focus I'm taking, is that the interchange in each of these points that we dealt with before, that's where I'm getting these points from. Okay. Thankfully, that's my focus because, as I said, I made the mistake in changing it to an x plus 3 when I shouldn't have. The good news is the domain part didn't change, right? I just messed up that what ended up being our vertical shift. Now, with that said, make sure do you see the symmetry here of these two graphs across y equals x? All right. Is there anything else I'd clear up here after straightening up my mistake? All right, so let's go graph another logarithm. Wrong thing. Simplifying it just a little bit. As y'all are finishing up writing down the function, what's something you definitely should highlight right now? All right, definitely make sure you highlight the 3, right? That's gonna be our focus. We're not gonna do 2 and 4 this time. What's powers of 3 that we want to use now? Right? We're gonna do 1, 3, and 9. Right? So keep that in mind as we deal with this. It's 1, 3, and 9. It's no longer 1, 2, and 4. Okay. Those are our powers of 3. With that said, though, as far as transformations, hopefully you see here, the only thing we have is the horizontal transformation. Okay, there's nothing's outside of the logarithm, so that's not going to be applicable to the situation. But as far as that horizontal, make sure again you're careful with that being an opposite, right? And so we're going to go to the left 2. With that though, what else did I say we should do with the x plus 2? All right. What are we not allowed to have in the argument of a logarithm? We don't want 0 and we don't want negatives, right? So make sure, like, when you state this, you could state the horizontal, I keep saying the wrong thing, state the vertical asymptote, right? There's nothing wrong with that. But I also encourage you to write out your domain, like, hey, x plus 2 better be greater than 0. I don't want 0 or negatives in here, which means that when I do that solving, I better be going to the right of that -2. Okay. So as far as this graph is concerned, make sure you see again, I'm going to start by doing the vertical asymptote that we just stated. Make sure you see that that's at x equal to -2. There is no shift up or down. Okay, so that's why I'm putting that little green random mark there, just kind of help focus myself here. Now, with that said, though, as we just mentioned, our domain here lets us know that, hey, we should be going to the right of -2. Okay, now I will say be careful here. This is definitely, if I don't ask you to graph it, I at least ask you to give me the domain on the test, because I feel like with logarithms, if we can focus on the domain, it helps us get into the correct steps of finding the domain. I mean, the graph, sorry. As long as we can get the domain, finding the graph, that helps a lot. So that's why you see here now, again, I went through that process of making sure to show that, right? Whatever argument is greater than 0, no zeros, no negatives. As far as the graph is concerned, right, one critical point that we always want to make sure to put, just go one to the right of wherever your focus is, okay? I'm not typically going to put a stretch or a shrink on it, so we could confidently say, hey, just go to the one to the right. Now, make sure, again, you saw, though, remember I graphed that exponential one where I think we started with what, $8,000 or $800? And when we zoomed out that graph, instead of one, it represented whatever the initial amount was. Okay, so keep that in mind. But from here, this is where our base becomes important. Okay, our base tells us that we should be going upwards. So this is going to be 3. And then the next one is going to be somewhere out at 7, right? So that's going to be our 9. Where am I getting that from? 3 squared and 3 to the first power. But because we're dealing with a logarithm, we're going up and to the right now, okay? Now, if you wanted to, you could definitely plot 1/3 and 1/9. There's nothing wrong with that, okay? It's not as nice as a 1/2 and a 1/4, though. But make sure you see here, the bottom approaches that asymptote. And we have that same kind of growth going up from there. That exponential pattern that we've seen in our graphs, okay? Now, make sure some things that we see here that we learned from our exponential as we approach this -2 here, right? So as x approaches -2, and we're coming from the right side here, it's never actually going to get there. Is that clear to everyone? It's never actually going to get to -2. So we have to be careful with that. All right. But make sure you see here, it just drops. It's going to keep getting closer and closer and closer, but never actually get there. So we'll just say, hey, it just goes down to -8, kind of like what we saw with vertical asymptotes of a rational. So it's very similar to a rational when it comes to dealing with the vertical asymptote. Okay. Questions or concerns here? All right, then. So some things that we do need to talk about then is some quick evaluations that we should be prepared for, right? As we deal with this, if you're plugging stuff into the logarithm, there's some things that we can run across that we want to be comfortable with. So I have some here that we can look at in the last couple of minutes just to make sure we see what we're working with. The one thing I'll encourage y'all to, as you practice this is one of those things that you want to spend some time doing these problems. If you need to do problems multiple times to get comfortable with them, you make sure you do that, right? This is definitely something new, and most of this is definitely gonna be on the final. There's usually 5 or 6 problems that deal with logarithms on the final. Probably more like 4, I get 4 or 5, sorry. So you want to make sure you're comfortable with the different things that we're seeing here. The domain, getting a graph, that's definitely one aspect, okay? As you see here, evaluating some things is definitely important. If I give you log base 5 of 5, what I'm saying is 5 to what exponent gives you 5. So what exponent would that be? 1, right? So if the argument and the base are ever the same, it's always going to be 1. This is true for any base. So log base A of A is 1. Okay. What's going on with log base 2 of 64, though? We got to do some work, right? Is the key, right? Understanding what I would recommend is if you're not sure, just go factor the 64. It will take some work, but this is definitely within the realm of your abilities, even if you have to use a calculator, right? The key is what do we want to count up when we get that factoring done? How many twos are there, right? Make sure it's only twos. That's definitely an important part. If any number gets introduced other than a 2, then we can't do it, right? But here, thankfully, we have all 2s, and as mentioned, we're going to have 6 of them. Okay. What's special about natural log e to the 5th? The base of a natural log, though, is e, right? It's very similar to what we just saw with log base 2 of 64. The problem is e to the 5th, we just leave as e to the 5th, right? There's nothing we can do with that because it's an irrational number when we're done. What you find here, though, is this is kind of like a power rule that we can use. So anytime you have a log with a base and the argument has a same base, so kind of the mixing of a logarithm and exponential, so log base A of A to some power, it's always going to be whatever that power is. That's only true, though, if the base of the logarithm and base of the argument are the same. So we have to be careful of that. Okay. Now, the good news is the power rule can be used when the bases are not the same, but we have to be careful how we write it. Right now, I could put in this case, 5, because it works well together. Okay. What you see is kind of this getting brought into the picture. What's going on with this one? So I have a common log, right, which we have to remember is base 10. The nice thing about 10,000, right, if I factor that down, how many 10s go into it? How do we know it's 4, though? The zeros, right? Just count up the zeros. Anytime you have a common log with a power of 10, just count the zeros. That's the nice thing about that. Now, it's not always, again, it's not always going to work out that nice. I could put 101 and you're stuck using your calculator. The good news is our calculator has the common log, right? So if you don't believe me, go put log of 10,000 in your calculator and you're going to get 4. Now, the TI 30, the Roger guy is those top, it was the top left, right? It was where the log and natural log were. So you could put this in your calculator, it's going to give you could even do natural log of e to the 5th, and it's going to give you the value that you're seeing here. Okay. Now, just out of curiosity, between the natural and common log, which one do you think we use more? That natural log. Even though we call it the common log, the natural log is typically what we see. Okay, so just keep that in mind. What is the log base pi of 1? So pi raised to what exponent would equal 1?
0.
Anything to the 0 equals 1. Okay. Make sure you remember that one. It's another important one, that anything, doesn't matter your base, right? If the argument is 1, it's going to equal 0. What do I do with the next one? The log base 7 of 1 over 49 that we have to be careful of. It's going to be a negative, right? We'll have 7 to what power gives us 49? All right, so just remember that's a -2. Okay, so that goes, the key again, though, remember the numerator is 1. So anytime the numerator is 1, I could just focus on the base and remember to put a negative exponent. Okay, that's one thing to be careful of whenever you deal with this. Hey, since that's just a 1 on top, well, what's this as a power of 7? Well, that's 7 times 7, right? I just need to make sure to put negative for my result. Okay. Now, this is another one that's fun that follows that kind of pattern, right? Where we start with something and we're getting a smaller number back. The difference here is, though, how would you describe getting from 8 to 2 when using an exponent? How many 2s do you need to make an 8? 3, but the problem is isn't log base 2 of 3, right? It's log base 8 of 2. So instead of 2 cubed, we need to do 8 And what do we need to do to the 8 to get to the 2? Division could work, but remember, we're trying to break this down through exponents, right? That's why we're thinking like, hey, this is 2 times 2 times 2. We could do 2 to the third, but remember, 8 is our denominator. Not our denominator, our base, sorry. 8 is the base. What operation is the opposite of a cube? So if I gave you x cubed equals something, what would we have to do to solve? A cube root, right? So understand that this would be like, hey, the cube root of 8 equals 2, right? Remember here, then what we need to do is say, hey, that's a rational exponent. Okay, not going to come up all the time. Please understand that, but this is definitely something you want to watch for is that, hey, I can definitely get to a situation where I need to think of a cube root or a square root, okay? Another example of that could happen would be like, hey, what if I gave you, say, log base 16 of 4? Well, what do you need to do to the 16 to get to the 4? Not a cube root, but a square root, right? But makes you understand we put that in the denominator, whatever we say, right? 1 over whatever I need, okay? Please understand, again, that's not going to come up all the time, all right? Now, this last one, put this in your calculator. That's what we want to focus on, okay? Be careful with your parentheses when you do that division. You got 6? Now, as we finish up today, I know it's time to go. Make sure you see here that I intentionally did that to connect these two together, okay? Huh? You got to use that log key in the top left. And then make sure you close your parenthesis and then do the division, okay? But as you walk out, please understand that we're going to do that a lot to be able to evaluate stuff. This is called the change of base formula. And make sure you go back to the one that we just did to see that, hey, log base 2 is 64 could have been done this way, okay? But have a good day, and I will see y'all tomorrow.